Hello and welcome back. In the last lecture, we have seen why FFT is so important. FFT is an algorithm to calculate DFT. Okay, so here we are going to see the DIT-FFT algorithm. We have two parts of FFT algorithm. So first one is DIT-FFT, decimation in time, fast Fourier transform. In short, it is called as DIT-FFT. And the other one is decimation in frequency. So what is decimation? Decimation is division. So we are dividing in time. So dividing the time domain sequence in some small part, and we are achieving the thing what we wanted to do. We wanted to reduce the computational complexity of DFT by breaking the DFT into smaller number point of DFTs. So we wanted to break 16 point DFT into 2 8 point DFT, then into 4 point DFTs, then into 2 point DFTs, like this. So why we want to break that? Because 2 point DFT is very easy to calculate. Computational complexity reduces because of that only. Because in the calculation only 1 and minus 1 is involved. Okay. So this FFT was found by two scientists named Cooley and Tukey in 1965. This algorithm is a bit larger, but I assure you that while watching this video, you will feel that it is so easy. Okay, so we first write the definition of DFT and start the derivation. So the definition x of k is equal to, for n points 0 to n minus 1, x of n, we'll directly write in terms of Twiddle factor the definition. Is a n raised to kn, where this k is varying from 0 to n minus 1. So it's an n point DFT. Okay. So first we want to divide this x of n into two parts, even index sequence and odd index sequence. So firstly we'll assume g of n is the even indexed sequence. So we can obtain it by x of 2n. Okay. So suppose these samples are x of 0, x of 2 and so on, x of n minus 2. Okay. You can put the values of n starting from 0 to n by 2 minus 1. In this x of n, you have all the samples x of 1, x of 0, x of 1, x of 2, x of 3. So you can get only the even sample when you put this to n. Then odd indexed sequence. This we assume that h of n is equal to x of 2n plus 1. You might know this. X of 1, x of 3, x of n minus 1. Again, you can put n values starting from 0 to n by 2 minus 1 to get these values. Okay. So first, before proceeding to the actual algorithm, but proceeding this definition, dividing it into two parts, first we'll see some properties of Twiddle factor. This is Twiddle factor. We'll see some properties of it and we'll proceed. So in one of my lectures we have seen, if a 4 point DFT is there, write like this. This Twiddle factor, omega 4 raised to 0, we start from here, omega 4 raised to 1, omega 4 raised to 2, omega 4 raised to 3. Similarly, this is equal to omega 4 raised to 4. This is equal to omega 4 raised to 5. Okay. So on. So this omega 4 raised to 0 is equal to omega 4 raised to 4 is equal to omega 4 raised to 8, like this. So this is one property. Omega n raised to k plus n plus 2n plus 3n, like this. this is equal to the same factor, same value. So it is omega n raised to k. So this property is called as periodicity property. Next, we'll see the values. So this value is 1, this value is minus 1, this value is j, this value is minus j. So if we are going to travel for 2 points, half number of points starting from this omega 4 raised to 0 plus 2. So we'll reach here. So we can observe that the sign is changing. Instead of 1, we are getting minus 1. So from this point, omega 4, 1, if we travel for half number of point, that is 2 number of point, then we'll get omega 4 raised to 3, that is equal to j. So minus j is changing to j. So always the sign is changing. From this point to this point, the sign is changing. Or you can see symmetrically opposite points are having negative sign. Okay. So we can write this property, omega n raised to k plus half number of points is equal to minus omega n raised to k. So this property is called as symmetry property. Okay. Now this is about general case. We have talked about 4 points. Now if 8 points are there, we divide this circle into 8 parts and we start. This point is equal to omega 8 0, this is omega 8 1, this is omega 8 2, omega 8 3, and so on. So you can see omega 8 2 is equal to omega 4 1, omega 8 2 is equal to omega 4 1, and this point also, and you can consider at this point, it will be easy to compare, omega 8 4. Okay, so this point will write omega 4 2 is equal to omega 8 4. So you can observe that this is halved, then this is also halved. Okay, this is doubled, then this is also doubled. Okay, so we can write this in general terms like this: omega n raised to 2k is equal to omega n by 2. If you divide this will be also divided. Okay, so these three are very important properties. First is periodicity, then symmetry property, and this third one property. Okay, so we'll start with the algorithm. So we'll divide the first into even and odd parts. So x of k is equal to n starting from 0 to n minus 1, where n will take even samples of x of n, omega n raised to kn, plus now odd part, odd, x of n raised to kn. Here I have changed nothing, I have just written n is equal to even and n is equal to odd. Okay, now actually we'll write this n starting from 0 to, there are half number of points in that, so n was varying from 0 to n by 2 minus 1, and this was x of 2n. Okay, so x of 2n, instead of n we'll write 2n. So here also we'll write 2nk, plus for odd, similarly we'll write 0 to n by 2 minus 1, x of 2n plus 1, n raised to, again here we'll replace it by 2n plus 1. Okay, just we have changed it to even, odd, nothing else. N varying from 0 to n by 2 minus 1, x of 2n, we'll keep this term as it is, plus we'll simplify this now, n starting from 0 to n by 2 minus 1 x of 2n plus 1 omega n raised to now 2nk into omega n raised to k. Now this last term omega n raised to k is not having the small n in it. So we can take this term outside this summation. Okay. So I'll write this at the top. I hope you have understood all the steps. So this is what we are writing x of k. X of k is equal to this part. Now we'll change x of 2n to h of n. Sorry, g of n, and this to h of n. So g of n was the even samples. N is varying from 0 to n by 2 minus 1. Now we'll use that definition to divide this to half. So this will also be divided by 2. So this will become n by 2 raised to kn. Okay. Plus this came out omega n raised to k summation n varying from 0 to n by 2 minus 1. Here it is the odd sequence. This is h of n. Again this n by 2 to nk by 2. N by 2 kn. So at this point we observe that this is a DFT which is n by 2 point DFT of g of n. So we can write it g of k, and this part is a DFT of h of n, which is also n by 2 number of points. So it is, we can write h of k. Okay. So here we can observe we have broken x of k into two small DFTs. So this is the magic of this FFT algorithm. Okay. So we'll write this formula. I'll write this formula on the top so I can use it. X of k is equal to g of k omega n raised to k and h of k, plus we can say that these two are, the k is varying from 0 to n by 2 minus 1. So these two DFTs are n by 2 point DFTs, and this will be periodic with n by 2 number of points. Okay. So here we observe that only half number of points are obtained for x of k. Okay. So full number of points we need to add we need to add k with n by 2 so as to get the next n by 2 points. So this x of k is n point DFT. These two are n by 2 point DFTs. That's why the difficulty is occurring. Okay. So we'll solve this difficulty also. For the next points, we can add x of k plus n by 2. Add n by 2 to k everywhere. So here plus sign is there, is equal to g of k. Now this, sorry, I have to add n by 2 to this. N by 2 plus this formula n k plus n by 2 h of k plus n by 2. Okay. Now this g of k and h of k, these both are n by 2 point periodic. Okay. So g of k plus n by 2 is equal to g of k. G of k plus n by 2 is equal to g of k, and h of k plus n by 2 is equal to h of k, as this is n by 2 point periodic sequence. Now we can write x of k plus n by 2 and directly write here x of k plus n by 2. The remaining half number of points is equal to g of k. Okay, now at this point g of k, and at this point we'll use the symmetry property so that the sign will get reversed, k plus n by 2. So we are traveling half number of points, so omega n raised to k h of k. So sign will be reversed in case of second half number of points. So I'll write it here, h of k, like this. Now these two are very important equations, so I have written this in the corner. So now using these two equations, here also k is varying from 0 to n by 2 minus 1. So these two are very important examples, equations. For first half number of points and second half number of points, we are going to use this. Now for illustration, we'll take n is equal to 8 case. So x of 0 to x of 7 samples will be there. First 4 points, then x of 5, x of 6 and x of 7. Okay, so x of 0 is calculated from g of 0, h of 0. G of 0 plus omega 8. Now we are specific with n, so I'm writing here 8 raised to 0, h of 0, g of 1. Now k is equal to 1. H of 1, g of 2, omega 8 2, h of 2, g of 3, omega 8 raised to 3, h of 3. So these are the first 4 equations. Now in the second 4 equations, g of k, h of k, so all the values will be same, just we are reversing the sign. Instead of plus, we are adding minus. So x of 4, k plus n by 2 means the next half number of points calculation is started here. G of 0 minus omega 8 0, h of 0. This is g of 1 minus omega 8 1, h of 1. X of 6, g of 2 minus omega 8 2, h of 2. This last point, x of 7 is equal to g of 3 minus omega 8 3, h of 3. So from this you can see these are the 4-point DFTs from which we are calculating this 8-point DFT. So here we'll draw this, how to calculate the final samples. So suppose this is x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. So these are the final output points. So output is obtained from g of 0 and h of 0 to 4-point DFTs, and this g of 0 is obtained from even index samples. So these samples are x of 0, x of 2, x of 4, x of 6. From these samples you calculate 4-point DFT and get G of 0. Okay, so I'll write G of 0, G of 1, G of 2, G of 3. Similarly, from odd index samples, we calculate. Odd index samples are x of 1, x of 3, x of 5 and x of 7. This is 4-point DFT. You're obtaining h of 0, h of 1, h of 2 and h of 3. And you're always multiplying h of k with this Twiddle factor. That is why I'm writing here this Twiddle factors: omega 8 0, omega 8 1, omega 8 2, omega 8 3, like this. So let us see the first equation. X of 0 is equal to G of 0 plus G of 0 plus omega 8 0 into h of 0, this point. Okay, so we'll connect this. So this is coming like this. So G of 0 plus this point is x of 0. So in case of x of 1, G of 1 and h of 1. So this point plus h of 1 into omega 8 1. So this point. Okay, likewise you can connect the lines for x of 2 and x of 3. Okay, these are all going upwards. So you are obtaining here half number of points. For the next point, just x of 4, we need G of 0 minus omega 8 0, h of 0. G of 0 minus this. So we need a minus sign here. So let us take a minus sign here like this and connect this line to this. This is coming downwards. Similarly, you can calculate x of 5. Here also you will need a minus sign. Similarly, you can calculate x of 6 and x of 7. Every time here you need a minus sign multiplying to it. So this is the stage 1. Stage 1. And this looks like a butterfly. Okay. So it is called as butterfly structure. Okay. So this is just the stage 1. This is very beautiful. This is dividing an 8-point DFT into two 4-point DFTs that we wanted to achieve. When we go for shorter point DFTs, we reduce the number of calculations. Now we don't want 4-point DFT here. We want 2-point DFTs. Okay. So from this equation, this is a general equation. From this equation, we can write equations for getting this 4-point DFT using two 2-point DFTs. Okay, so I'll rub these equations. So suppose for doing this, dividing this 4-point DFT into 2-point DFTs, we need to again divide this inputs. Again, we need to scramble this. So we will find even points and odd points for the even sequence. Again, even points and odd points for the odd sequence. So we have G of n, even sequence. We'll make two parts of it. G of n, suppose we write it P of n, Q of n. So it will contain the sample x of 0 and x of 4, two samples. Q of n will contain these two samples, x of 2 and x of 6. So we'll call it even, and this part is even odd. And for h of n, odd sequence, we'll make again two parts, r of n and s of n. So this odd even part and odd part. Okay, so we are dividing again the samples. Okay, and we'll see what happens. So here we can look, P of n can have a transform, we call it P of k, and Q of n is having transform Q of k. R of n, S of n will have transform R of k and capital S of k. Okay. So we'll write just the equations for G of k. How to obtain G of k from this P of k and Q of k. Okay. So G of k, so it is n by 2 point DFT. Okay. So G of k is obtained from P of k and Q of k. P of k, as this is n by 2 number of points, so here I have to write n by 2, n by 2k, not h of k. I'll write Q of k. Okay. And this is for k varying from 0 to n by 2 minus 1. So for n is equal to 8, this is starting from 0 to 1 only. So this is first half number of points. For the second half number of points, we have to reverse the sign. But before that, we'll change one thing. We don't want here n by 2. So I'll make it n. So we have to make it 2k. So for next half number of points, that are g of k plus n by 4 is equal to p of k minus, here I have to write n 2k q of k. This is again k varying from 0 to n by 4 minus 1, n by 4. By mistake I have written n by 2, but it's n by 4. n by 4 minus 1. So 1 by 1 I'll write equations for this g of 0, g of 1, g of 2, g of 3. I'll write the equations here for simplicity. I need to extend this graph on this side. So for g of 0, g of 1, g of 2 and g of 3. We'll write the equations here. G of 0, P of 0 and Q of 0. P of 0 plus here the factor omega n raised to 2k. So omega 8, 0 versus 0. Q of 0, G of 1. For this value of k is equal to 1. P of 1 plus omega 8 now raised to 1. So it will become 2. Q of 1. For the rest of the 2, we'll reverse the sign. P of 0 minus omega 8, 0 this equation. And P of 1 minus omega 8 raised to 2. Q of 1. So these 4 equations are there. Simply we'll replace this part. Now I'll rub this part also. I'm not writing the equations for h of k because you can similarly write the equations for h of k also. So I'm writing like this. Okay. Now how g of k is obtained? G of k is obtained from, this is a 2-point DFT, this is again a 2-point DFT. So this input sequence is also scrambled. X of 0, X of 4, X of 2, X of 6, X of 1, X of 5, X of 3 and X of 7. So from this even part, so we are calculating this. So first is P of 0, P of 1, Q of 0, Q of 1. Similarly for H of, we'll have 2, that is R of 0, R of 1, and this is not R, this is S. S of 0 and S of 1, and at these point as Q's, we are multiplying it by the two factors omega 8 0, omega 8 0 and omega 8 2. Here also omega 8 0, omega 8 2. Okay, so we'll proceed. G of 0 is calculated from P of 0, Q of 0 multiplied by omega 8 0. Okay, so from this point we are going like this, and G of 1, G of n is calculated from P of 1 and Q of 1 multiplied by omega 8 2. So this is that point, this plus this, like this. Now similar to the last time, we have to just multiply it by minus sign when we are going downwards. P of 0 minus omega 8 0, Q of 0. This is G of 2. Okay, so here we have to multiply it minus 1. Also for G of 3, the multiplication by minus 1. Okay, so this is a short butterfly. This is the second stage. You can say stage 2. Here I can complete the second part also like this. Without writing the equation, you can guess how it is done. Now you know that 2-point DFT is very simple to calculate. So you have matrix like this, 1 1 1 1 minus 1. So if a point is like this, input is like this, the output is like x1 x2. So you have to obtain x1 by adding those 2 points, x1 plus x2, and x2 you obtain x1 minus x2. So calculations are so simple for 2-point DFTs. So here, instead of writing this 2-point DFT, I can draw a butterfly like this. First let me complete the lines. And a minus 1 here, minus 1, you know how the flow is going. This point plus this point minus this point plus this point minus this point, like this the flow is going. So just I'll write here omega 8 0. This factor is 1, but I'll write here omega 8 0, omega 8 0, omega 8 0. So this is how the calculations are. And this last stage is stage 3. So 8-point DFT is calculated in 3 stages like this. So this is called as butterfly structure for calculating the fast Fourier transform. Okay, so you can observe, instead of matrix calculations, by using this graph, the calculations are so easy. So you can calculate, go on calculating for this stage, then for this stage, then for this stage. You have to do that many of calculations only. Okay, so in the next lecture we'll see how much the computational complexity is reduced actually. We're saying that this is reduced. This is reduced, but how much? So we'll see by taking the numbers. We'll compare the DFT computations and FFT computations. Okay, formulas for that, and also see the other advantages of using FFT. Okay, thank you.